Hello class, today we're going to go over 11.4, the comparison test, and exactly what you're thinking is what we're going to be doing here. So we're going to be comparing, so let's get to it. So an example of what we're going to do is something like this. So if I gave you a series, a series that was like this, this isn't so simple for us to do, but we do know something about this. We can compare it. So I know that 1 over 2 to the n plus 1 is smaller than 1 over 2 to the n, right? Because the denominator is bigger for the 2 to the n plus 1, so that's going to mean that overall that's going to be smaller. We know that the one on the right is a geometric series and it converges to be equal to 1 because our radius of convergence is less than 1, less than or equal to less than 1. So we know it's going to be convergent and that value ends up being equal to 1. So we know that the value that we have on the left is going to be less than 1. So that means that would also converge. So this is what the convergence is going to be doing for us. So in the comparison test, it talks about two series, right? Some series with a sub n terms and the other with b sub n terms. And the first one says we have convergence if the bigger term converges, then the smaller term must also converge. Basically, we're going to take something that's bigger, and because it's bigger, we're going to be able to show if it converges, then the other converges. That's what I did up here. This was bigger than this. Since this converges, this also must converge to something. On the other side, if we have something that's bigger that diverges, right? If we have something that's smaller that diverges, then something that's bigger is also going to diverge. So the opposite's going on here. So as the smaller one diverges, the bigger one has to diverge also. So that's what this is saying here. So let's show an example of this so you guys can better understand it. So with this problem here, I can compare 5 over 2n squared plus 4n plus 3 to just 5 over 2n squared. And you agree that 5 over 2n squared is going to be bigger because the denominator of it is smaller. So that means that it's the same number divided by a smaller denominator is going to obviously be bigger. So then what we can show is then our sum of this 5 over n squared is going to be equal to 5 over 2, the sum going to infinity of 1 over n squared. And we know that this is convergent, right? And the reason we know that this is convergent is because this is a p-series. And it's a p-series that has its p equal to 2, which is bigger than 1. And we know from p-series that makes it convergent. And since this is bigger and converges, by default, therefore, our series, our sum of our series, right, is going to be convergent. So we know that it's going to go to some value. That's what the comparison test is telling us to do. Let me show you another example. Maybe this will help a little bit. But you can see that from doing the comparison test, this means that you know a lot of your series. So it's important that the homework from 11.3 is done and understood. Knowing those series will be very, very important. Later on, I'll give you a list of series with their convergences so you can see. But as of right now, you're going to be referencing to 11.3 a lot. Okay, so in this example here, we have ln of n over n, and we're trying to find out if this converges or diverges. Well, one of the things that's important that we need to know is that ln of n is going to approach, or is going to be bigger than 1 when n is bigger than or equal to 3, right? Because if we plug in ln of 3, it's going to become a 1, right? 1 point something or other, and then everything after that is going to be bigger than 1. So then I know that I can compare ln of n over n, and that should be bigger than 1 over n for my n greater than or equal to 3. And again, that's because of what I just showed you. And so comparing the smaller side, right, I'm going to go n equals 1 of 1 over n. I know that this is divergent, right? And this is again by the p-series. And since it's divergent by the p-series, p is equal to 1, right? It's to the first power. So if this, which is smaller, is going to diverge, that means therefore that my sum of something that's slightly bigger is going to have to also diverge. So you can kind of see what the divergence test is telling us here. Basically see something that's going to be relevant to it and then go from there. And the thing is here, right, we're going from 1 to infinity, but 1 and 2 are just something that we're going to add to something that's divergent. So if something that's divergent is going to have something else added to it, it's just going to be even more divergent. And by divergent, I mean it's either growing forever or it's decreasing forever, right? It's not going to some specific number. All right. Let's look at this next thing, and this is the comparison test. And when you do the comparison test here, you're going to be comparing two series that are positive terms, and if you see that the two positive terms are equal to some constant, and that constant is positive, then either both series converge or both diverge. So what it's telling us is that both are going to converge or both are going to diverge if it comes up to some constant number, right? And if that c is greater than 0, that's the important piece that's going to let us determine these ratios. So let's look at it. And again, it's comparison, so we're going to be basing it off of something that we know. So if we know one converges, then the other one's going to have to converge. If I know the other one diverges, then the one that we have has to diverge. So in this example, we've already kind of worked this one out. I know my a sub n is going to be 1 over 2 to the n minus 1. So my b sub n is going to be 1 over 2 to the n. And so it's the fraction of these two, right? So I'm going to take the limit as n goes to infinity of 1 over 2 to the n minus 1 over 1 over 2 to the n. But we know that this is going to be 2 to the n over 2 to the n minus 1. And so this here is going to be dividing top and bottom by 2 to the n. I'm going to get 1 over 1 minus 1 over 2 to the n. But when I apply the limit here, oops, make sure you guys can see that, I'm going to get 1 over 1 minus 0, which is going to give me 1. And that's my c. My c is 1. That's greater than 0, right? And since that's greater than 0, we're going to be able to determine that this thing is either going to be convergent or divergent, right? And the thing that we do know already is that 1 over 2n is a geometric, right? It's a geometric series. And since it's a geometric series, we know that it converges, right? And since it converges, that implies that the series that we are comparing also converges. So because I knew this one was geometric, I knew that it converges, right? And since it converges, the one that I'm comparing it to, since the constant, the ratio of their constant was greater than 0, it also had to converge. So that's going to be the trick with these problems. As you see them, you're going to have to find ways to be able to compare them. So let's see if I can give you some more examples so you guys can kind of get an idea of what's happening here. Okay, so in this next example, this looks kind of freaky, right? Like, we obviously know our a sub n is going to be our 2n squared plus 3n over the root of 5 plus n to the 5th. And our b sub n is just going to simply be the first term, right, the b to the n squared. And then in the denominator, I'm going to take that n to the 5th divided by 2, right, because it's a rooted function. But this is going to be able to be cleaned up to be 2 over n to the 1/2. Okay, so now we're going to do a ratio to this thing, right, just like the comparison test told us to do. So I'm going to have the limit as n goes to infinity of my 2n cubed plus 3n over the root of 5 plus n to the 5th, all over 2 over n to the 1/2. Well, this can be cleaned up, right? It can be cleaned up. And what I'm going to do is when I divide by a fraction, I multiply by the reciprocal. So I'm going to get 2n cubed plus 3n over 5 plus n to the 5th rooted times n to the 1/2 over 2. And this should also be able to be cleaned up a little bit. So I'm going to go n as it goes to infinity. And I'm going to get 2n to the 5 over 2 plus 3n to the 3 over 2. That should be a 3 there. Over 2 root 5 plus n to the 5th. And that, as we apply, is going to be the limit as n goes to infinity. And now what I'm going to do is I'm going to divide by n to the 5/2, right? So I'm going to get plus 3 over n over 2 root of 5n squared plus 1. And then this right here, when we apply the limit, we're going to see we get 2 over 2 root 0 plus 1, which is going to give me 2 over 2, which is 1. And so from here, we can see that the comparison again is greater than 0. And again, we can see that this is going to converge. All right? Because we know that the our b term 2 over n to the 1/2 is going to converge, so this also converges. Okay, let's do another example. And in this example here, we see that the sum of the first 100 terms, we're going to use the sum of the first 100 terms to approximate the sum of the series. Estimate the error involved in this approximation. So the first thing that we're going to do is we want to find something that we can compare it to, and we can see, all right, 1 over n cubed plus 1 is clearly smaller than 1 over n cubed, and we know that 1 over n cubed is convergent. So that tells us that what we have here is something that is going to be convergent. And so some notation that we're going to use to be able to solve this is going to be t sub n is going to be less than or equal to from n to infinity of 1 over x cubed dx. And we know that when we take the integral of 1 over x cubed, we're going to end up with 2 to the n squared. And then what's going to happen is we're going to have an error or a remainder of this thing, this potential error, that's going to be this 2 over n squared. And now what we need to do is look at the first 100 terms. So if we have 100 terms, that tells us that our n is 100. And so we can see something that's pretty cool here. We're going to get 1 over 2 times 100 squared. Let me use a calculator to figure this out. So 1 divided by that's going to give me I forgot the 2. So that should give me 0.0002. And so that's going to give me something that's pretty cool, because this is the error that we're going to have. And so we want, if we're going to get an error for this thing that's going to be accurate, to, let's say, to 3 decimal places, we'd want 3 zeros to be put there, right? And so there's 1, 2, 3 zeros. So this tells me that this is going to be accurate to 3 zeros. So in using a program, I have a TI-89 for this. I can tell you what the approximate value of this is. I can show you when we're working in class how to do it. That's approximate. How to plug it into your calculator to try and do this, we'll discuss that in class. So this is going to be this approximate value is going to be 0.686538, and we're going to have an error. This should be a 5, not a 2. We're going to have an error that's with an error that's less than 0.000405. So there should be one more 0 here. Is that right? Let me make sure. I want to retype that into my calculator. I don't want to misinform you. So 2 times oh yeah, 0.004. So that is another 0 there. And so we can see that we're going to be very, very accurate here, which is so good. This is 11.4. The stress to this this section really is about understanding what to compare to. So, and you can kind of see it, right? So like in this example, we see that if I get rid of the constant here, it's going to be 1 over n cubed. In this example here, I took the highest term in the numerator over the highest term in the denominator and then compared them. That's how I ended up with this. Same thing here, right? If I get rid of the constant, it's just going to be 1 over 2n. That's a geometric series. And then in this example here, this was the one that took a little bit of manipulation. I wanted it to be 1 over n. But since ln of n is growing, I needed to stress to show that this was going to be bigger than 1, so that then this ratio was bigger than this ratio. That's the crux to the comparison test. I hope you find this helpful. As we do homework problems together in class, we can further discuss and better understand how to do these problems. All right, wish you all the best. Take care.